Okay, so we're going to start using this Euler characteristic tool to start trying to figure out what graphs could be planar and what graphs could not. We're not going to actually develop a complete answer with that tool alone. There is a theorem that tells us which graphs are planar and which ones are not, but it's not an easy to use theorem. Okay, at least not in all cases. All right, so let's kind of bring back something that's super important here, and let's do an example. Just kind of review what the Euler characteristic was, and so we also have an example in front of us to play with. All right, so just draw like a hexagonal figure here, maybe. And then maybe I'll connect here. Okay, again, you could do another example that's unique to you. Just make sure there's no edge crossings. Remember, we're envisioning drawing this on a sphere, or that's the context in which we're playing with this, but remember, we generally draw on boards and paper, and so the terminology planar or on a plane is also appropriate. It just means we convert it over. All right, now we should be able to count certainly the vertices and edges. That's fairly easy, and then being able to count the faces is important. All right, and this would always be a mistake, right? There's something missing here. Don't forget the outside face. When you're drawing on a plane or a piece of paper, it's always going to have this weird outside face, but if it was on a sphere, it would just be another region on the sphere in addition to these four. So there's 5 total. All right, so the Euler characteristic for this, let's have to count the vertices, and there's 6 of them. Let me go and give this a name. Oops, I don't need parentheses on there. Call this thing G. And we often say the Euler characteristic of G, but we'll get a little bit more crystal clear in how the Euler characteristic graph might be defined. Right, because as it stands, this is really going to be the Euler characteristic of the surface it's on, provided it divides it into faces, vertices, and edges. Right, so I'll repeat that. The Euler characteristic of G here isn't really the Euler characteristic of the graph. What we're really measuring is the Euler characteristic of where it's placed, provided it properly separates it into vertices and edges and faces, right? The hard one being faces. All right, so in this case, it's B minus E plus F always. And in this case, 6 vertices. We have to count the edges in this case. I don't see, well, actually, no, you could use the sum of degrees, but let's do both maybe. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Count 9 edges. If you look at this, it's 6 times 3 is 18, divided by 2 is also 9. So, all right, then plus 5. Minus 3 plus 5 is 2, right? And at this point, hopefully it's not unexpected. You're kind of expecting to get 2. Okay. Now, this sort of relationship between the vertices, edges, and number of faces is constrained to being 2 if we're going to insist that we draw this thing on a sphere or a plane. And let's use that. Okay. So we're going to need to talk about face degree. Okay. So what is that going to be? This is going to be pretty important here. All right. So the degree of a face is the number of times it is incident with an edge. Okay, this is all of them together, right? Okay, all incidences, which is hard for me to say. All right, so let's look at an example. Okay, and I'd like to, well, let's have a slightly different color here. Let's do the degree of each of these faces here. All right, so in this example, it's actually incredibly straightforward, and I don't think we would get different answers even if we were trying hard. So the degree of this first face, well, you can see it's touching 4 edges, and so its degree is 4. Okay, faces number 2 and 3, they're surrounded by 3 edges or touching 3 edges, so they get degree 3. All right, now let's look at 4 here. It's a little more deformed, but 1, 2, 3, 4. So if you go around, and this is kind of what I would suggest you do, and if it starts getting complicated, take a tour around the boundary, and just notice how many times it says, oh, that's an edge, that's an edge, that's an edge. Okay, so that looks like 4. Right. And then 5, take a tour around the outside here, and it looks like it's also 4. All right. Let me use this color because it's the one I did degrees. Let's add these up. 4 plus 4 plus 4 plus 3 plus 3. 12, 15, 18. Okay, now if you look at the sum of the degrees of the vertices, I only did it verbally. If I did it with the vertices, it was 3 plus 3 plus 3 plus 3 plus 3, 3, 4, 5 plus 3. Also 18. So check it out, each of the 6 vertices has degree 3. Right? Which I said out loud, but now it's written down. So we're getting 18. It turns out this is true. The sum of degrees of faces, or this is, of course this is true, but the generally it'll be true that the sum of degrees of faces and the sum of degrees of the vertices are equal. So here's the theorem. So the sum degrees of the faces is equal to twice the number of edges. All right, if you want an equation for this, it kind of fits neatly in. Sum degree of faces is 2 times the number of edges. Take the faces in G, but of course G has to be embedded on a surface and form faces, right, there's some implicit stuff. It's not just G by itself, it's G on a surface without edge crossings. Very important. But once you have that, you can add up the degree of the faces, and you should get 2e. Alright, now I'm not going to prove this one because the proof is basically identical to the other one. Here's the change. Alright, so we did the sum of degrees for vertices, and that worked because each edge has 2 ends. Right? There's an end to each edge, and that provides the incidence to the vertices. Now, when we do faces, every face has 2 sides, and so that's the only thing you have to change. Right? So instead of having 2 ends, now we're looking at it from the perspective of an edge having 2 sides, and you get the same result for all the same reasons. Okay, and this comes back to why I keep saying the sum degrees theorem is probably the most important theorem in here, because it has a twin, and that is this thing in terms of faces. Alright, I have just enough room to fit a kind of small example, but a good one that starts to get your notions of this kind of ironed out. It can be a little strange to do this sometimes, so let's take G and make it a little bit more unusual. Alright. I really only have to add a little bit to make it unusual, and then we'll be good. Okay, so here's our graph G. It has 2 faces, inside and outside, if those names seem appropriate. Right? And we should be able to count the degrees. So let's start with kind of the easy one, and that is the outside. Right, so the degrees of the outside is just 4. It's a degree 4 face. Okay? And you can starting to get this in your mind. The outside of this thing is a square, right? It is functionally a square. The inside, what's the degree of that face? Usually if I ask the class for answers, I get 2 answers, and I get a lot of 5s, and then I get some people that say 6. And 6 is the right answer. So think about this. So again, go around. There's 1, 2, 3, 4, 5, 6. Okay, so you can see it is incident with this edge twice. It is doubly incident with it. Okay? And in fact, this face, if you think about the edges connecting together faces, which we will encode in the next video, we'll talk about that and make another graph for it. This face is actually adjacent to itself through this edge. Okay, so faces are adjacent to one another through edges, right? So this face is face 4 is adjacent to face 1 through this edge, right? Well, turns out this face is adjacent to itself there. Okay, so the number of degrees here is 6. So the degree of this interior is 6. And yes, you can think about this thing, the interior of this being a hexagon. That's pretty accurate. It's a weird hexagon, but you can see, think about taking a flexible piece of paper, maybe you can think of it as like some other material, maybe rubber or something, and you have a square, but then you cut it in the middle, then you're able to kind of stretch it out. Well, you could pull this apart right here, and you could actually form it into a hexagon. Okay, so take a moment to think about that. Be creative, think about cutting, make that cut in there, and it adds a way for you to make 2 more sides. Okay, and then you can kind of let this kind of go nuts, right? You can start doing some fairly bizarre looking versions of this. Right, you can start making little trees inside of graphs. Oh, hopefully this color isn't so bad. So I do like these little Y shapes. See, as a challenge, what the degree of the inside is. It's pretty high. I'll do it, just give you an answer, but if you want to pause and see if you can do it. So draw a triangle and put these little Y trees. The outside has degree 3. While you're working, or before you get an answer, or maybe after you get an answer, the degree on the inside, does it have to be even or odd? And the answer is it has to be odd, right? It's going to be this degree plus this degree has to be an even number. So if you count wrong, hopefully you're only off by 1, and so knowing that it's odd will protect you. So let me see if I can count it up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. I got 21. Okay, and I can actually see if this is right. So my sum of degrees is 24, which tells me I should have 12 edges. And if I have 12 edges, I'll be confident that I counted it right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, I feel good about that. That count there. And you can be creative, think of some other examples if you want. But that inside face there is very complex, right? If you were to actually make these as cuts into these faces, you could actually open this up into a 21-sided polygon. You just have to kind of stretch it there. So again, I keep saying this, but this is not a bad metaphor. If you want to think about your graph as actually a division structure that forms these regions into individual faces that can be pulled apart, that's not a bad mental tool, right? And then you can glue these faces back together, and the graph is sort of the encoding of the way the faces are assembled. Okay, so next thing we're going to do in the next video is talk about something called a duality structure. It's called the graph's dual. And it has to do with planar graphs. This is very specific to planar graphs, but it's another perspective on encoding how faces are adjacent to one another. All right, so I'll see you on that.